All right, last time we were working in section 4.3, in fact, the last couple class periods, and we haven't quite finished it up yet. And we're working on this idea of greatest common divisors and least common multiples, although to this point we've still been working on the first part of this, which is the greatest common divisor part. So where we are so far is we talked about what divisors are, and we've talked about a few methods for finding those. Let's see, we have looked at the first one we actually looked at was intersection of sets, where we wrote out the different method, or the different, all of the different divisors and simply looked for the largest one. That's great as long as the numbers are small, right? And then we talked about prime factorization, where we did either factor trees or this division, sort of an algorithm here, where we looked at what prime factors they had in common, and then those combined and multiplied back out would be the greatest common divisor or greatest common factor. This one right here, we actually looked for only prime factors they had in common and divided them by those. And the last one was the sort of awkward, weird one that we maybe said it looked sort of hidden or fuzzy as to where this was coming from. It was called the Euclidean algorithm. And when we did this one, we were looking at dividing the larger number by the smaller number and using that remainder with the divisor on the outside to do that again. And then the last number that we divide by when we get a remainder of 0 is the greatest common divisor. So those are the different methods we had for greatest common divisors. So today we're going to finally start the least common multiples part. And you'll see that some of these actually look a lot like the same method. And there's very good reason for that. So we'll discuss that as we go. So just first what we're going to talk about is what a least common multiple is. So a least common multiple is, and we mentioned this once before, is that this word least or this word greatest is an adjective that describes what comes next, right? It's an adjective describing that noun. And so the fact that it says least does not mean it's necessarily a small number. As a matter of fact, it has to be at least as big as both the numbers you're already working with. Okay, it can't be any smaller than the numbers you're already working with. So least common multiple is typically a large number. So jot that down to yourself. So when you're finding a greatest common factor or a least common multiple, a greatest common factor is smaller than a least common multiple. It's just the way it works, okay? So a least common multiple is the least number that is a multiple of all the numbers in the set. So if you were taking a look at these, or one way to think about these, is using a number line method. So a number line method, or sometimes called a colored rods method, shows all the multiples of number on a number line in the intervals of each value. And then you find the first value where they have that in common. So the first thing I'm going to do is I'm going to create a number line. We've worked with number lines before. And as I create this number line, I'm going to do two different pieces to creating that. Let me do this first. So I'm going to start at 0. And because I have a number line that has the number 6, because I have a problem that uses the number 6, I want to take sort of jumps of 6 along the number line. Right? That's multiples of 6. So we wouldn't have to draw a picture for this, but this is one way to think about it. We could also simply list out the multiples of 6, and it would have that same sort of effect. But I want to show you what it does on the number line first. So if we go from 0 to 6, and then what would we end on? What's next? 12. And then what? 18. And then what? 24. And then what? 30. And I'm going to do a couple more. What's after 30? 36. And the next one? 42. So those I'm labeled because I know I'm going to need those values for sure. And what I'm going to do is I'm going to use a different color. And I'm going to make, in fact, let me make it this way. I'm going to make arrows of length 6. So this piece right here is 6 units. So I'm sort of making that jump of 6. And then I start where the last jump of 6 ended, and I make another jump of 12 to 12. And then the next line, that wasn't good, let's try again, goes to 18, 18 to 24, 24 to 30, and so forth. So I draw all these arrows that represent these jumps along the number line. Now, the other number that I have doesn't include these same numbers, at least not all of them. The other number is the number 15. So if I were working with the number 15, and I take one jump, I jump to the number 15. Well, 15 would be halfway between 12 and 18, so it's right here. So let me change my color, and what I'm going to do is I'm going to have a number line arrow here that goes from 0 over to 15 now. Because this jumps 15 long. And if I jump another 15, where do I end up? At 30. It's not quite the way I wanted it to look. I wanted it to look straight, but it's not working. All right, so if I jump from 15 to 30, I end up here. That's 36 too. I'm sorry. Let's try one more time. Maybe I get it to, probably not. You guys see it bouncing. Do you see it bouncing? Okay. It's not my imagination. All right, so we're jumping from 15 to 30. The answer to the least common multiple then is the first place where both of the arrows end. Okay, so you notice, like, for instance, at the 15, I'm in the middle of the 6, the red lines for 6, but I'm not at the end of an arrow here. So that's why the answer is not 15, is because the arrows don't match up at that point. It's not, I'm in the middle of a jump, right? The jump that goes between 12 and 18. Whereas when I get to 30, I'm actually at the end of a jump. So sort of imagine that you had frogs that were jumping, and one of them was a frog that could jump 6 inches, and the other was a frog that could jump 15 inches, and they were along the same path. Well, the first place that both of them would land would be at 30, right? That's the first matching location where they would land. Everybody have a picture of what's going on? So this is a really good visual for what's going on here without using specific numbers. All right, let's do another example. This is an intersection of sets method. So this is what I was describing when I was describing the last one. So this one actually creates a list of multiples of each number. Okay, so the last example would work really well when you're introducing this idea with small numbers, right? You can make these jumps of 6 or 15 or whatever. But once we get to 12 and 15, I don't want to make this diagram from the last example for very long, because these don't have a number in common as quickly as the 15 and the 6 did. But what this method does is it actually has us list out multiples. We had another method where we listed things out. When we did that method, though, we were looking for what? We weren't listing multiples. What were we listing? Factors. So we listed all the factors out of what divided that value. Here I'm listing multiples. So the first multiple of 12 is actually 12. And I think Beck and I talked about this multiples idea in the last section when we were talking about listing these out. And I said, well, think about multiplication tables, right? If you were doing the multiplication tables, what would come after 1 times 12 is 12. Then you'd get 2 times 12, which is 24. What's your next multiple? 48. And then? Oh, we missed one. You're right. Let me get 36 in there. And then we'll do 48. What's after 48? 60. And then? 72. Let's do one more just for fun. 84. Lovely. We have that same 15 from the previous example. So they always start with the number 15 because it's itself times 1. What comes next? 30. And then? Let's just do one more. 75. Okay, good. As soon as you find a matching pair, you can stop. I actually went one beyond, but what matches? 60. This is the least multiple that they have in common. These are all multiples. Multiples of 12, multiples of 15. The one they have in common that is the least is the number 60. So the least common multiple here is 60. I didn't write it over here. Perhaps I should have. The least common multiple in your previous example would have been the number 30. Any questions on that method? Okay, so again, that would be okay as long as they fairly quickly have a common multiple. That doesn't always happen, right? So we're going to do a prime factorization method. Well, that again sounds like something we already did, doesn't it? In fact, the first few steps look exactly the same. They say we're going to construct the prime factorization for each number. We're going to look for the common prime values. But then what's different is in step 3. What does step 3 say that's different, if you can flip back in your notes, to step 3 of the last prime factorization method? What's different? You use the largest exponent instead of the smallest exponent. And there's actually one other thing that I sort of glossed over in step 2 that's slightly different. Can you compare those step 2s? Right, so Marilee, you said this word all is different, right? In fact, I even kind of said it wrong when I was reading it. I said common, and it's actually not the ones they have in common, although those get included. We actually include all the prime factors, even the ones they don't have in common. So let's take a look at what this looks like when we're working with it. I'm using an example this time that has 3 factors. or sorry, 3 values that we're finding the least common multiple for. But that works the same way for 2 values or 3 values. So I want to show you that in general that what I'm doing actually can work for multiple numbers, not just 2 pairs of numbers on this one. All right, so let's do 90. And I'm going to do the same method that I did before. So smallest prime number that divides 90, 2. And then that gives me 45. Smallest number that divides 45. And what does he get? What do you get when you divide that by 3? Good. Number that divides 15. Another 3. And then I get a 5. Okay. So let's just kind of leave this one at this point. We'll come back to him in a minute to get that information. Let's go on to the next one, 50. Smallest number that divides 50. 2. What do I get? 25. Smallest that divides 25. 5, and I get 5, and I'm done. The last one is a 20. Smallest number that divides 20. And if I divide that, I get 10. Smallest number here, 2. Division is 5. Okay, so these are all down into their common, or into their broken down into their prime factors now. So what I want to do is I'm going to actually write these out to the side. You don't have to do this, but I want to show the identification step very clearly of what we've got here going on. So if 90 is 2 times 3 squared times 5, 50 is 2 times 5 squared, and 20 was 2 squared times 5. Everybody good so far? This is using the last section of material to do that, right? All right, so what we're looking for is, on number 2, it says choose all the prime factors. So the least common multiple does not just use the ones they have in common, because if it was looking for the common factors here, what's in common? 2 and 5. 2s and 5s are in all 3 of these. But there's another number that's included that's not common to all of them. It's the number 3. So when I'm looking for least common multiples, I include the 2, the 3, and the 5. But then what does it say I'm going to let be the exponent here? The largest one that any of them has, right? So taking a look at these, what is your largest exponent on any of these for the number 2? 2. How about your largest exponent on 3? Happens to be a 2. And the largest exponent on the 5? Also happens to be a 2. All right, so broken down into prime factors, this is the least common multiple. We're going to actually work this out to what the value looks like multiplied out. So 2 squared is 4, 3 squared is, and 5 squared is 25. So let's multiply that out. What do you get when you multiply 4 times 9 times 25? It is 900. If you're looking for an easy way to multiply this, this is actually one of those strategies you've seen before. 4 and 25 are compatible numbers because what did they multiply to be? 100, and 100 times 9 is your 900. All right, so you could check to make sure this is a common multiple. How? How could you make sure this is a common multiple for this problem? Yeah, I could make sure that if I tried the 50, the 90, and the 20, that they all actually divide the 900, right? And do they? Yeah, they do. So this is at least a common multiple. We know it's the least common multiple because we used the least exponent possible to include everything. That's why it's the least one. We used the smallest thing we could include that includes everything. All right, there's one other one here that's really nice, and this is the prime factors method, and so the division by primes method, rather. And you've seen this before, too, haven't you? You've seen that phrase, division by primes? We did that one with greatest common factors. And it works the same way. We write the numbers in a row. We look for common prime factors. But there's a little bit of a difference as we continue. So we're going to start it just like we started when we did this problem before. So we're going to write the 90 and the 100 and the 20 all out. And we're looking for prime numbers that divide these. What's the smallest prime number that divides all 3? 2. 2 works. So 90 divided by 2 is? 100 divided by 2 is? And 20 divided by 2 is 10. What is the next smallest number that divides all 3 of these? 5. 45 divided by 5? 50 divided by 5? And 10 divided by 5? Here's where this comes different. If you were finding greatest common divisor, you would be done, right? There are no numbers that divide all three of these anymore. Everybody agree with me on that? Okay? So the greatest common divisor would actually be 10, because it's these two multiplied. However, when we're working with least common multiples, we continue the division if any of them still have common factors. Two of these numbers do still have something in common, don't they? What numbers? 2 and 10. So the way this works is that we're doing one more division step. It will be the last one on this particular one, though it wouldn't have to be. And I know that the 2 does not divide the 9, so I simply write the 9 down again. So I recognize that we did not divide it. That's okay. All right? This is not for finding greatest common divisor. It will work out all right. But we do divide the pieces that still can divide. So the 10 is divisible by 2, and I get a 5. And the 2 is divisible by 2, and I get a 1. And then what we're doing when we do the least common multiple is I multiply everything along the edge and the bottom. Because the bottom, none of those pieces, 9, 5, and 1, have any factors in common any longer. So you're done with this division by primes when all of the numbers on the bottom have nothing that are going to divide any two of them. Nothing in common any longer. So your least common multiple here is 2 times 5 times 2 times 9 times 5, and then technically times the 1. So somebody multiply that out for us and let me know what you get. You do get 900 again. Yeah. Any question on that one? Yes.
On the last one, on the 9.
Here? Mm-hmm.
Yes. On the 9, why didn't we divide? Well, I mean, can you explain the 9 and the 2 again and why you wrote 9 down?
Here's what we're really doing when we do this last step by dividing by 2, is we're recognizing that the 10 and 2 still have a factor in common. If I don't divide out one of them, that is eliminate one of them, I will end up with a common multiple, but it won't be the least common multiple. So by dividing by this 2, I eliminate that duplicated factor that they both had in common. But see, the 9 didn't have it, so we just sort of ignore the 9 for now. So if it doesn't divide wholly by the number that you're working with, then you just write it down again. And you're done at the last step when I got this 9, 5, 1. Simply not, and it's not because these numbers are all prime, although the 5 is prime, and the 1's not prime, but we could sort of ignore that and say, yeah, but it's 1. 9's certainly not prime. So there's nothing about getting to this last step that said, look, now they're all primes. That's not the point. The point is they don't have any factors in common, and that's how I know I'm at my final step. Yes, Morgan?
Could it ever be where you do that and then you'd have to divide again, like with the 9 still?
Yes. Yeah, it could be. So, like for instance, let's say that this 9 were not a 9 at this point here at the very end. Let's say it were a 45, right? So could we have to then divide the 45 and the 5? Absolutely. Yeah, you could have to do that at that step. So that is looking at 2 different factors to see if they have common factors. Yeah, you could. All right. There is a wonderful relationship that we keep sort of skirting around as we've been working. The relationship is the greatest common divisor and the least common multiple formula. They are related. Well, they should be, because these methods are nearly identical, weren't they? I mean, I almost did the same thing every single time. I just looked at the answer in a different way. How do I get my answer? It's done in a little different way, but I did all the methods the same. So how in the world are these related? Well, the reality is that when you multiply the greatest common divisor of 2 numbers, we'll call them A and B, by the least common multiple of those same numbers, A and B, it's the same thing as multiplying the 2 numbers together. In other words, if you already found the greatest common divisor, you could use this formula to find the least common multiple. And vice versa. All right, we did this problem once before. I'm going to do it again, I think, since it was last class period. When we did this problem, we did it with Euclidean algorithm. So let's do that again, just to go through it, because it's been a couple days. All right, so the Euclidean algorithm, do you remember how we do the Euclidean algorithm? So I'm going to do the Euclidean algorithm to show this. What do I do with the Euclidean algorithm?
You divide the smaller to the larger.
Right, so smaller one goes on the outside, larger one goes underneath, and I say how many times does 72 go into 126? Once. And then I use my wonderful division with some subtraction in there, and what's my remainder? 54. Okay, what's next in this algorithm? Take the 54 and the 72, and what do we do with them? We do 72 divided by the 54, right. And it goes in one time again, right? What's 72 minus 54? 18. Okay, if this feels like something you've done before, it's because you have. We already did this once before, but I'm reminding you. And then what? You take the 54 and you divide it by the 18. And 54 divides by 18 exactly 3 times with no remainder. And the fact that I get no remainder here tells me that my greatest common divisor is the last number I divided by, 18. All right, so in terms of the formula up here, which is actually what this question was asking me to do, was to use this formula. What I know is I know that if I take the greatest common divisor and multiply by the least common multiple, I should get the same value as if I multiply the two numbers I'm working with, in this case 72 and 126 together. That's what that formula says. These notation right here with the parentheses and the AB, that's not a multiplication. That's just saying using those two numbers. If I find the greatest common divisor of A and B, it's just notation telling me which two numbers I'm considering finding the greatest common divisor of. Okay, that's what that notation means. So you found the greatest common divisor. It was 18. And I'm fairly certain you guys can multiply 72 and 126 for me pretty quick, right? I see some calculators, so I know somebody can. What's 72 times 126? What'd you get, Becca?
907.
9072? Okay. How do I find the least common multiple then? Divide each side by 18. Thank you, Hannah. So, Becca, can you do that since you did the last piece still in your calculator?
504.
So because I know that my greatest common divisor is 18 from previous problem, basically, I can now find that my least common multiple is 504 simply by dividing. Any questions on that? And that would work for any of them. I didn't have to use the Euclidean algorithm as the very first step to doing that. So if we went back to division by primes over here, 410 and 360. 410 and 360 had a greatest common divisor of 10. So how could I find their least common multiple? Right, I could find the least common multiple here by multiplying the 410 times the 360 and dividing by the greatest common divisor, which is 10. I wouldn't have to go any further with the steps. I wouldn't have to multiply the 41 and the 36 or see anything else. I can just simply multiply these two numbers together and divide by their greatest common divisor, and I will find their least common multiple. So that's kind of a handy trick. All right, let's do a couple more examples in this section that kind of show how this idea is used in real life or practice. The numbers we're working with are going to be smaller to deal with, which is a little bit more realistic for our real world examples. But we've got two bikers, and they're going around a circular path. The first rider completes one round in 12 minutes. So imagine a track. Okay, this is like a circular track. One of them can go around the path in 12 minutes. The other one goes around the path in 18 minutes. Everybody with me so far? So they're both riding in circles, round and round and round. One of them does a full lap in 12 minutes, the other one in a full lap in 18 minutes. If they both start at the same place and at the same time, it's a race or something like this, it's an event, start at the same place and at the same time, after how many minutes will they meet again at the starting place? Okay, so every time around, there's some assumptions in here like they're not slowing down. I recognize that. But if the pace stays the same pace, that's what the problem is indicating. So first person goes around the track and they get back to the starting spot in 12 minutes. And if they keep going, when's the next time they get back to the starting spot? 24 minutes. And the next time they go back around the starting spot to 36 and so forth. Everybody with me? Player number 2, whatever, rider number 2, does the same thing, except that he goes around and he ends up back at the starting spot in 18 minutes. And if he goes around again, it's in 36 minutes. So what we're wanting to know is how many times do they have to keep spinning around and around the circle before they both end up at the starting spot at the same time. So my first question to you is, do I need to find a least common multiple or a greatest common factor? Good. Very good, guys. This is a least common multiple problem because I'm making multiple trips around the track. I mean, that's really what's happening, right? This is a least common multiple application. So you've got lots of methods for doing this. These numbers are fairly small, so you really have the whole gamut of options. How do you want to do it? Do you want to do some factoring? Do you want to do some list making? Do you want to draw a picture? Somebody give me an example. List? Lists? Okay, I hear a couple people saying list. All right, so if I do lists, in fact, we've sort of started generating these lists. We'd already said 12 and then 24. Where's the next time that this particular person ends up back at the starting spot? 36? 48? 60? And you may not know where to stop, so if you want to stop and then try the other list and see if you've already hit the number, you can do that. Let's try the other number, which is 18. So if I do 18, the first lap's in 18, and the second lap's in 36. So I actually went farther than I needed to, because what do you see? The 36, right? So there's a couple questions. The question that they actually asked us is, after how many minutes will they meet again at the starting place? 36 minutes is my answer. What if I wanted to do a follow-up question that said something like, how many laps did each of them make of the circular path? What would you say? One of them made 2 laps and one of them made 3 laps, right? We could answer that question as well using this sort of a list method. Any questions on that one? This is an application of least common multiple. And you'll see some applications with greatest common divisor in your homework, in your group work. The last example, example 11 says, can 2 non-zero numbers have a greatest common multiple? Explain your answer. Good. The answer is no. Okay, so what do you mean by infinite numbers? Okay, so the numbers aren't infinite. What's infinite? The list of multiples, right? So the answer is no, and it has to do with this idea that the list of multiples, and I'm not going to use the word infinity because I don't want you to think of the word infinity as though it's meaning I can get anything large, because I can't. I only still get multiples. But the list of multiples continues forever. So like imagine on the last problem, if they keep going around this circular track indefinitely, like they continue to do this forever, they will keep crossing at the starting spot every 36 minutes, won't they? I mean, one guy crosses after he makes 2 laps, the other guy crosses after he makes 3, but they always cross after they've both ridden 36 minutes. So they'll cross at 36 minutes, and then they'll cross again at 36 minutes after that, which is 72 minutes. And they'll cross again at 36 minutes after that, and they'll keep doing this. This pattern will continue because this list of multiples continues forever. So we can do an example if you'd like, and we can think about, let me say it this way. In example 10, that's the previous one we just did, the bikers across at the starting line. Every 36 minutes. So at 36, and again at 72, and I'll just put dot, dot, dot after that. So this list of common multiples is an infinite list, right? Because the list is infinite, it doesn't have an ending spot on this particular list. Make sense? All right.